Okay, so today we will start the fourth unit, that is unit 4, and it is the stiffness matrix method. Stiffness matrix method. Okay, so in this just a moment. Now, is this screen visible to you properly? Which one is visible? This is visible
Yeah,
now?
yeah, visible, sir.
Okay, so I'll teach in this one because this is not that much appropriate. So I'm erasing everything. Okay. Okay, so today we will start the new topic, that is Unit 4. Unit 4, and in Unit 4 we have the stiffness matrix method. Okay, so basically the flexibility matrix method and the stiffness matrix method, these two are are based on the matrices. Okay, so I'll directly go to a problem because all of you are till now aware with what is the definition of stiffness, what is the definition of like when you call material to be stiffness and all. Okay, so we will directly go to a continuous beam problem. Okay, so that you can easily remember the things how to solve these kind of problems. Okay, so please take down the first problem for unit 4, and this is the problem. So write down problem 1. Analyze the continuous beam as shown in the figure below. Using sorry, this is again the same one, the stiffness matrix method. Also draw the shear force and bending moment diagrams. Okay, so how does the figure look like? Okay, how the continuous beam looks like. So one end is fixed, one end, the intermediate one, is hinged, and the extreme end is also hinged. Okay, and we have a UDL of magnitude 120 kilonewton per meter, and we have a concentrated load of magnitude 200 kilonewton. Okay, now the length of this span is 4 meters, and the length of this end till this load, it is 1.5 meters, and this one is also 1.5 meters. This is A, this is B, this is C. Okay, and the I value is here, it is I, this one is also I. Okay, this is the problem. So now remember one thing, guys, that whenever you have been asked about the problem, is if the problem is based on the stiffness matrix method, okay, then you just remember that in the first step you have to determine the degree of kinematic indeterminacy. Do you remember what is the formula for degree of kinematic indeterminacy? We have learned in the starting class. Okay, so how to find the degrees of freedom, or what is the formula to, or how to determine uh, the degree of kinematic indeterminacy of a structure. So the same procedure we will follow is here. Okay, so here whenever we solve using the stiffness matrix method, so basically here what we do is we will consider the displacements as unknowns. Okay, so here, so you just remember there is I'm making a table. This is only for your rough understanding. This is not any kind of formulas or something. Okay, so if it is a stiffness matrix method, sorry, if it is a stiffness matrix method, here you will take the displacements as unknowns. Displacements as unknowns. Okay, and if it is a flexibility matrix method, in flexibility matrix method, what you take as unknowns or redundants? Anyone? Harshvardhan? In flexibility matrix method, what do you take as unknowns? Or what do you consider as redundants? It will be forces, or it may be the moments. Okay, the redundant moments we consider this. Okay, so here we will consider the displacements to be the redundants or unknowns. Okay, now, so please pay close attention here. Okay, so now this end A is fixed. Okay, so here since end A is fixed, we will be having three reactions over here. Okay, so what reactions? One will be vertical, one will be horizontal, and one moment will be generated. Why? Because these three, so displacement in this direction, displacement in this direction, and rotation in this direction is restricted. So that's why here three reaction components will be there. Now here one will be this one, another will be the horizontal one, reactions will be there. Here one, and here also one horizontal component will be there, definitely. Okay, moments will be zero here. Okay, so here what we need to do, so all of you I think all of you remember, wait, I think all of you remember that. Okay, let's go to the first step so that you can remember that one, or recall that one. Step 1, the step 1 here is degree of kinematic indeterminacy. Okay, so here the degree of kinematic indeterminacy, let us say that is what we call Ki. Okay, Ki or simply I. Let us call it as I. Okay, so I I equals to, or you may call it as Ik. Okay, so Ik equals to total number of unrestrained degrees of freedom minus number of restrained degrees of freedom. freedom. Okay. So now what is the total number of unrestrained degrees of freedom? See, whenever I told a beam element or any node, okay, or any node or any joint. So at any joint we have 3 degrees of freedom. So one is a vertical movement may be there, a horizontal movement may be there, one rotation will be there. Okay. So at every joint we have 3 degrees of freedom. So this means that we have 3 degrees of freedom here, 3 here, 3 here. Okay, so totally how much? So 3 into number of joints. Okay, so 3j minus r. Do you remember this formula? So either you can go by total number of unrestrained degrees of freedom minus restrained degrees of freedom, or you can go by 3 into j minus r. Okay, so j is the number of joints. So here what is the number of joints? Okay, so
2, sir.
3. So j is the number of joints and R is the restrained degrees of freedom. Let me write number of sorry, R is the number of restrained degrees of freedom. Okay, so this J is, so number of joints is 3 into number of joints is 3. Okay, now what is this capital R? Capital R is the number of restrained degrees of freedom, means at where or what are the degrees of freedom where the displacement is restrained or restricted. Okay, so here since this is a fixed end, okay, this is a fixed end, so here we will not have any displacement in this direction, neither we will have displacement in this direction, neither we will have any kind of rotations here. Okay, so here we have got 3 number of restrained degrees of freedom. Similarly, due to this hinge joint, okay, the displacement in vertical direction is restricted, the displacement in horizontal direction is restricted. Similarly, due to this hinged support, here at node C or joint C, the vertical displacement is restricted and the horizontal displacement was also resisted. Okay, so R becomes, so here at joint A it is 3 plus at joint B it is 2 plus at joint C it is 2 again. So totally the value of R is 7. Okay, so 3 into 3 minus 7. So it is 9 minus 7, that is 2. So hence the degree of kinematic indeterminacy of this structure is 2. So here we can write hence the degree of kinematic indeterminacy for the continuous beam problem is how much? Is 2. Okay, so just like the flexibility matrix method, we have one equation that is to be satisfied. Okay, so now what is that equation? That equation is F equals to K into D. Okay, now what is this F? F is the force vector here. Okay, K is the stiffness matrix and D is the displacement matrix. Okay, and remember one thing, that this the size of this matrix will be ik. Okay, so ik cross 1. So this will be ik cross ik, or let us say this is the size of this matrix, or let us say the size of this matrix will be n cross 1. This will be n cross n, and this will be n cross 1. Okay, so I'm writing it in red once again, n cross 1, n cross n, and n cross 1. Okay, now what is this n? N is this one, so n equals to ik. Okay, so this means that for this current problem, F will be a matrix of size 2 cross 1, K will be of a matrix of size 2 cross 2, and D, that is the displacement matrix, will be of size 2 cross 1. Okay, that is the thing. Okay, now further, just like the okay, so further this F matrix will be Fi minus Fl. Okay, now what is this Fi? Fi equals to the internal forces or the direct movements. So if anything is, see, Fi, so what do you mean by this Fi is, if instead of this force here, if any movement is given at the joints or at anywhere, okay, that is to be considered there. Okay, next, Fl is the, what is Fl? Fl is the moment at the coordinates. All of you please mute your mics. Okay, now what is Fl? Okay, or what is okay, Fl we will understand. So see here, so now, so here this, okay, just tell me one thing, that how this beam will deflect, or where the displacement of this beam will be there. Who can tell? If this is the beam, okay, here the beam is restricted in this direction, and in rotation also it is restricted. Here it is restricted in vertical direction, it is also restricted in horizontal direction. Here this one, so these two are restricted. Okay, so these two, this value 2, okay, this value which we found, that is the degree of kinematic indeterminacy, or the degrees of freedom will be, so here it will be, here one displacement. Okay, so here at this joint we will have one rotation, and at this joint we will have one rotation. Okay, so these are the two coordinates. Okay, so let us redraw that figure here. So here at this is one, this is another one. So here this is A, this is B, this is C. So the coordinate 1, sorry, this one, let me take. So the coordinate 1 will be here, and the coordinate 2 will be here. Okay, so it means that we will apply unit rotations here in order to determine these two rotations. So these two rotations are unknown here. So these two rotations we need to find it out. Okay, so this is theta theta b and theta c. So theta b and theta c are unknown. Here theta is 0 because this is theta a is 0. Why theta a is 0? Because a is what? Fixed end. Okay, so this theta b and theta c we are supposed to determine. Okay, so theta b and theta c will be here. So this D matrix D equals to D1L, D2L, that is the displacement matrix. So that will be theta B and theta C. Okay. Now, what about this force matrix? Okay. So write down. So we have to determine the force matrix, that is. So write down step 2. Step 2, that is fixed end moments. Fixed end moments. Okay, now if you see this figure over here, so or it is better if I draw a figure here one more time. Okay, so this is the figure, this is fixed, this is hinged, again this is hinged. Okay, we have this one is 120, we have a concentrated load 200 kilonewton. This one is 1.5 meters. This is also 1.5 meters, and this is 4 meters. This is A, this is B, and this is C. Okay, so please find out what is MFAB, fixed end moment. All of you, I think you remember this one. What is MFAB, or how much is MFAB? So MFAB equals to minus W into L square by 12 or 8? 12. So it is minus W. So W is 120 kilonewton per meter here. So minus 120 into L is 4 square divided by 12. So that becomes minus 160 kilonewton meter. So similarly, MFBA equals to WL square divided by 12. So it is 120 into 4 square divided by 12. So that becomes 160 kilonewton meter, and this is positive. Okay, so similarly here in MFBC, so MFBC equals to minus WL by 8. So it is minus 200 into L is this total length is how much? 3 meters, right? So into 3 divided by 8. So that becomes minus yes, that is minus 75 kilonewton meter. So similarly, MFCB equals to WL by 8, that is 200 into 3 divided by 8, that becomes plus 75 kilonewton, sorry, not kilonewton per meter, it is kilonewton meter. Okay, kilonewton meter. Okay, so we have determined MFAB and MFBC plus MFCB. Okay, so now we know that the force matrix F equals to, I told, Fi minus Fl. So since there is nothing here, okay, so it will be, so again, since L is of size, what is the size of FL? The size of FL I told as it, or F I told as it should be 2 cross 1. Okay, so similarly F I1 Fi2 minus F1L minus F2L. Okay, so since there is no externally applied moments at any joints, okay, so it means that these two values will be 0. Okay, there is no externally applied moments and all. Okay, neither externally applied moments nor force, anything. Okay, now there are no externally applied direct moments. Okay, so we need to determine F1L and F2L. Okay, so now what is F1L? So F1L is the moment, sorry, F1L is the moment at here. Okay, summation of the moment at here. So F1L, I am writing it, F1L equals to, so F1L F1L equals to MF, this is BA, MFBA plus MFBC. So how much is MFBA? MFBA is 160. MFBC. MFBC is minus 75. So minus 75. So that becomes, so F1L equals to 85 kilonewton meter. Now F2L will be, so F2L will be, since this is coordinate 1, this one we are saying this is coordinate 1, this is coordinate 2, so moment here generated is only due to MFCB. Okay, so that will be MFCB. So how much is MFCB? MFCB is plus 75. So it is plus 75 kilonewton meter. So the F matrix becomes, so F equals to minus F1L minus F2L. Okay, so minus F1L means minus 85 kilonewton meter, and sorry, not minus 85, it is sorry, yes, minus 85 kilonewton meter, and it is minus 75 kilonewton meter again. Okay, so that is the F matrix, okay, or the force matrix. Okay, next in the step 2 we need to, okay, so before we go to the step 2, just pay attention here. So we have determined F force matrix, we have also determined the displacement matrix. Now the remaining is the stiffness matrix, that is K. Okay, so now in step 3 we will determine the stiffness matrix. So if we go to step 3, so here I can write step 3, that is the determination of the stiffness matrix. Okay, so remember that the size of K is n cross n or I K cross IK. So n is, how much is n? N is 2. N equals to 2, we got the degree of kinematic indeterminacy. So this is K11, K12, K21, K22. Okay. Now, what is K11? Okay. You may ask, sir, what is K11? Okay. So K11 equals to the force developed at coordinate 1 due to unit displacement applied at coordinate 1. Okay, so we know that in this present problem, this is A, this is B, this is C, and this one is coordinate 1, and this is coordinate 2. This is coordinate 1, this is coordinate 2. So the force developed at coordinate 1 due to the unit displacement at coordinate 1 itself. Okay, so here we will apply unit displacement. Okay, similarly, K12 equals to force developed at coordinate 2 due to unit displacement at coordinate 1. Okay, now, so what does this mean? So we need, okay, so we mean to say that what we intended to do is we will, let us say this is the given beam. For example, this is the given beam. So in order to find out this one, we have to make all the supports as fixed supports. Remember, okay, this is case 1. Okay, so here I am writing it as case 1 also. Okay, so here in case 1 we will find out K11, K12. Okay, so this is A, this is B, this is C. So instead of this hinge support, what we did, we made these two supports as fixed supports, and here we will apply unit rotation. Okay, unit displacement. So here, since it is not able to move in vertical and horizontal direction, this one, okay, only it can rotate. Okay, so what I need to do, what I will do is I will rotate this one. So how I will rotate? So here I will, since it is fixed, there will be no slope here. It will rotate like this, and again it will come, it will rotate, and again it will be, the slope will be 0 here, and it will reach here. So it means that here this one is theta b, that is 1. This is also theta b, that is also theta b, this is also 1. So here theta a equals to 0, and here theta a equals to 0. Sorry, not theta a, theta c equals to 0. Okay, so this K11 will be, so K11 equals to, so when I apply a moment, or I apply a rotation of one magnitude here and here, so it means that definitely there will be forces developed in this coordinate 1. Okay, so this one, so K11 will be, so if it is, so this end is far in, this is also far in, so the forces developed in the far ends will be 4. So let us say this length I am talking is, this length is L1. Let us say this length is L2. L2. Okay, so K11, if it is here, okay, if if we are determining the forces at coordinate 1, when the unit displacement is applied at coordinate 1 itself, then it will be 4 EI by, sorry, not EI1. Okay, let us say this is I1, this is I2. For example, in the question it is given. So 4 EI by L1 plus 4 EI2 by L2. Okay, so this will be 4E into, what about I? I is I, and L1 is, how much is L1? It is 4 meters and this is 3 meters, right? So 4EI by 4 plus 4EI by L2 is 3. Okay, so total you will get it as 2.33 EI. Okay, so similarly, this is, so since this is coordinate 1, as I told, this is coordinate 1 and this is coordinate 2. Okay, so at coordinate 2, due to this unit rotation, what is the force developed here? So that will be, so K12 equals to 2 EI by EI by, it is, or E to EI2 by, it is L2. So it is 2 EI by L2 is 3. So this becomes 0.67 EI. Okay, so this one is for case 1. Okay, now the next step is case 2. So the case 2 will be, so here we can write case 1 is apply unit rotation at coordinate 1. Okay, this is case 1. Case 2 is apply unit rotation at coordinate 2. So now just remember this one. Okay, so now, so this was coordinate 1. Now again I will draw the same figure. This is fixed, this is B, this is fixed, this is also fixed. Okay, this is A, this is B, this is C. Okay, so now what I will do, I will apply a coordinate moment here and or rotation here, and since this is fixed, it will be 0. Okay, so here what I can say, this is my, this one is my theta C equals to 1. This is theta B. Here will be theta B will be 0 because this is fixed end, and theta A is 0 by default here. Okay, so now this, so just like K11, K12, what are the other things left? That is K21, K21 and K22. So K21 will be forces developed in coordinate 1 due to displacements or unit displacements at coordinate 2. So similarly, next we have is K22, that is forces developed in coordinate 2 due to unit displacements at coordinate 2. Okay. So now for this K21, okay, for this K21, remember that this K12 and K21 will always be equal. Okay, so K21 equals to 2 EI. This I told as I2. This is I2. This is L. Oh, sorry, I1. This is L1, and this is L2. Okay, so 2EI2 divided by L2 for this problem. Okay, so this is 2EI by L2 is, how much is L2? L2 is 3 meters, it is given, so it is 3. So it is 2EIL by 3, or 2EIL or 2EI by 3. So this is same, this will be same as that one, so it is 0.67 EI. Okay, and K22 will be, so K22 will be forces developed at coordinate 2 due to unit displacements applied at coordinate 2 itself. So it will be again 4EI2 by L2. So it is 4E. I2 is I and L2 is 3 meters. So this becomes 0. It is 1.33 EI. Okay. So now we can say that the K matrix or the stiffness matrix is K11, K12, K21, K22. Okay. So this becomes, so K11 is, how much is K11? K11 is 2.33 EI. This is 0.67 EI. This is 0.67 EI. And this one is 1.33 EI. Okay. So now you can see here that we have determined so for this current problem we have found out the F matrix, we have found out, we have computed the K matrix, we have computed, or we are find out the D matrix. Okay, so now this displacement matrix is to be found out. Okay, that is this one. Okay, this is the unknown. Okay, so this one we will determine or we will find out in the next class. Okay, so that's all guys.